Okay, let's try a proof. So here we go. You got a picture. They're telling you that angle 1 is congruent to angle 3. And they're telling you that AC is parallel to BD. So there's too many lines. I'm gonna draw AC and BD. So here we go. This is AC, this is BD, my proof. These are my statements, my arguments. And this is my reason. Okay, AC and BD are parallel. And then they're telling me that angle 1 is the same as angle 3. So I want to show that AB is parallel to CD. So I want somehow to show that the top and the bottom are parallel. Okay, I can show the top and the bottom are parallel if I look at angle 1 and 2. So here's my transversal right here. So angle 1 is right here, angle 2 is right here. If I can somehow show that angle 1 and angle 2 are the same, then AB would have to be parallel to CD because 1 and 2 are alternate interior angles, and alternate interior angles are congruent only on parallel lines. So that's what I want. I want to somehow show that 1 is the same as 2. So I'm going to start off by saying angle 1 is congruent to angle 3. And how do I know that? That's what's given. And then I'm going to say that I'm going to state both of these, check, check. In my next move, I'm going to say AC is parallel to BD. How do I know that? That's given. Okay, now I've got to link 3 to 2. And if I'm looking at A, C, and BD, and I draw this bottom line, the CD, 3 is right here and 2 is right here. So I know A and B are parallel because that's given. So if they're parallel, I know this. 2 is the same as 3. So angle 2 is congruent to angle 3, and that is because they are corresponding. And corresponding angles are only congruent if the lines are parallel. So 3 is the same as 2. And if 1 is the same as 3, and 3 is the same as 2, that must mean this. That must mean angle 1 is congruent to angle 2, because if 1 is equal to 3 and 3 is equal to 2, 1 must also be equal to 2, and that's because of the transitive property. And then 1, if 1 is congruent to 2, that must mean AB is parallel to CD because alternate interior angles are congruent, and that only happens in parallel lines. Okay, the bottom, determine if R and S are parallel. So these two right here, I want to show that they are or they're not. Okay, this angle right here, this 92, if these lines are parallel, then these two together have to be 92. I need to kind of delete this diagonal line. So I just need to look at R and S, and there's my transversal. Or no, I want to delete that one. That's not the one I want to look at. I want to look at this vertical one. So this guy right here is 92. So this one at the top must be 92 because they're alternate exterior angles. So if 65 plus 27 is 92, we're in business. It is, so yes, because alternate exterior angles are congruent. And that only happens in parallel lines. Okay, this next one, oh, it looks a little tricky. So same thing, I want to show R and S are parallel. So here's my transversal. If I look at R and S and I just look at this bottom horizontal line, I want to see if I can show that this angle and this, so it's the same thing, alternate exterior. So 23 and 75, that's going to be 98 degrees. And then 57 and 41, that's also 98. So the answer is yes, same reason. Alternate exterior angles are congruent. Okay, so that's kind of it for the geometry. Now back to quadratics. acceleration. So on the surface of Mars, constant acceleration increases by 12 feet per second every second. So suppose you're 500 feet above the surface of Mars. What will its instantaneous speed be at 12 seconds? So every second in the air, it increases by 12. So I'm just going to do 12 times 12. At the end of that 12 second, it's going to be going 144 feet per second. So what's the distance traveled between the 12th and the 13th second? Okay, so the 12th second is going to be going 144. So this is second, and this is speed. The 13th second is going to be going 13 times 12. Speed is 156. So I'm just curious about this interval right here, the distance. And the distance is the speed times the time. But the speed is changing. But because the speed is changing at a constant rate, we can take the average speed. So the average speed of 144 and 156, the average speed I think is going to be 150. So if I take that average speed and times it by time, which is just 1 second, so the distance traveled just between the 12th and the 13th second is going to be 150 feet. Okay, now the total distance after 13 seconds. So the total distance after 13 seconds, now I gotta compare 13 from the very beginning. So the very beginning, 0, the speed was 0. 13, it was going 156. Okay, now the average speed between 0 and 156 is going to be a little bit slower. And because I'm comparing with 0, I just divide it by 2, add them up, divide by 2. So my average speed is going to be 78 feet per second from 0 to 13 seconds. So I'm going to take the average speed, 78, and I'm going to multiply it by the distance it was traveling, or the time that it was in the air, times 13 seconds. So 78 times 13, and that total distance is going to be 1,014 feet traveled. Okay, so when is he going to hit the surface? Now hopefully you've had enough experience. It's actually going to be easier if we do E. So how high? He's only 500 feet above the surface, so it's going to be well before 13 seconds. Okay, so let's do E first and then let's do D. Let's use the model to figure out when that it's going to hit the surface of Mars. Okay, the model. The distance, there's kind of two formulas. Distance as a function of time is going to equal, it's quadratic, ax squared plus bx plus c. And remember, a is it's the kind of the average rate of change. So you take this 12 and you divide it by 2. So it's going to be 6x squared. So that is the distance right there. That formula will give me the distance traveled at any second. So if I plug in, for example, if I plug in 13 and I do 13 squared is 169, and I times that by 6, that should give me the same answer, 1,014 feet. So that is the formula. Now I'm going to subtract that distance, so I'm going to make it negative from 500. I guess I could do 500 subtract the distance fallen. And I want to know when this is going to equal 0, because this spits out distance, so I want it to spit out a 0. And so I've got negative 6x squared plus 500 equals 0. You can do the quadratic formula A is a negative 6, B is 0, C is 500, and this will give you the exact. So if I ask you to the nearest thousandth of a second, this will give you that exact information. If you kind of just make a table or look at the graph, you can kind of guess maybe it's between like 6 and 7 seconds or something. But if you want the exact down to the thousandth or 100,000th of a second, the quadratic formula will give it to you. Now here's kind of a trick. If you are missing the bx, which we are, so we've got the ax squared and we got the c, but we got no bx. If you're missing the bx, it's easier and faster, instead of doing the quadratic formula, to just do inverse operations. So if you minus 500 from both sides, now you got a negative 6x squared equals negative 500. And now just divide by a negative 6, divide by a negative 6. So you've got x squared equals a negative divided by negative is a positive. 500 divided by 6, and then undo the square, square root. So your answer is going to be plus or minus square root of 500 divided by 6. Hit enter, and it is going to hit 0. And I'm going to ignore the minus, I just want the plus, at 9.128709 blah 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 seconds. So that is exactly the moment when it's going to hit the surface of Mars. Okay, another problem. This is on Earth. The gravity causes objects to accelerate 32 feet per second every second. So same types of problem. What's its average rate of change from 0 to 5? At 0, it's going 0 at 5 seconds. I'm going to do 5 times 32. And that speed is 160. So now I've got to find distance is rate times time, but because my rate is changing, I'm going to use the average rate. And the average between 0 and increasing all the way to 160 is going to be 80. And I've got to times that by how long it was in the air, which is 5 seconds. So 80 times 5, or I guess, hold on, it just wants 80. It just wants the average rate of change. So 80 feet per second. And if you times it by 5 seconds, that's going to travel 400 feet total it covered. B, average rate from 4 to 5 seconds. Okay, so don't compare 0. Let's compare 4. So 4 times 32 gives you 128, and 5 was 160. So the average speed between 4 and 5 seconds is faster than 128, slower than 160. It's right in the middle. 128. Whoa. Uh-oh. Holy cow. It's going to be 144. So the average speed from 4 to 5 seconds is 144 feet per second. What's the total distance traveled at 5? I think that's what we answered at A. The average speed times 5 seconds, so that's going to be 400 feet. When's it going to hit the Earth? It's going to hit the Earth. How high is it? Okay, it's 800 feet. So the distance is going to be a quadratic model. The distance depends on time. So every second in the air covers more. And it's going to be a quadratic model. My quadratic model is ax squared plus bx plus c. A is half of the gravity and the acceleration, so A is going to be 16. X squared, and x represents seconds. So there we go. That formula will give me the total distance traveled. So I just answered E. This is the answer to E. So if I want to know when it's going to hit the Earth, I'm just going to do 800, subtract the total distance, and I want to know when it hits 0. So negative 16x squared plus 800. And again, I'm missing the bx, So I'm just going to do inverse operations. I'm going to minus 800, minus 800. So I got a negative 800 equals negative 16x squared, divide by negative 16, divide by negative 16. And then you've got 800 over 16 equals x squared. Undo the square root, or undo the square, so square root both sides. So the square root of 800 over 16 is going to give you exactly D. It hits the Earth at 7.071067 seconds. So approximately close to 7 seconds. And I think I answered F. Write a model that gives the distance the object is above the surface of the Earth. That's this one right here. That's this guy right here. So its distance above the Earth at any second, you just take the distance traveled, make it negative, and add it to 800, and that will give you its position above the Earth. So, I didn't do any initial speed. So remember this, in the quadratic model, in this case, C is kind of where you start, or the height you're dropping. So C at 0 if you're dropping it. So the object's falling. So C would fall from 800 feet. That's 800. This is the y-intercept. This is whatever the mate of 0 is. A, that's half of your acceleration, because we're taking the average. So you add it between that and 0 and divide it by 2. So 32 divided by 2, A is going to be 16. And B is the speed that you start out at. Initial speed. And if you drop it, your initial speed is 0. But if you shoot an object or throw an object, then its initial speed is it's going to start out with something. So we've got 3 patterns, and I think I might have messed up on one of them. Let's go this first one. So 3 tables come up with the quadratics form. So first you got to look and see how it's changing, and it looks like these are shrinking. So it starts at 2000, goes to 1994. So that's a change. It went down 6. And then you just do 1994. This one went down 18. Then 1976. Whoops. This one went down 30. Probably one more. You don't need to do them all, but you got to do enough to figure out the pattern. 1946 minus 1904. Minus 42. Okay, now, so it's not changing at the same rate every time. Looks like it's increasing a little bit. So 6 to 18, that's a difference of 12. 18 to 30 is also a difference of 12. 30 to 42 is a difference of 12, but they're kind of negatives because it's getting smaller, smaller, smaller. So this is the planet you are on. The planet you're on, objects increase, accelerate every 12 feet every second. So my A, I know it's quadratic because your second change is constant. And now all you got to do is find A, find B, find C. A is half of that, so A is going to be a negative 6. C is easy to find. A and C are pretty easy to find. C is going to be 2000. Okay, now I'll show you a way to find B. If you know A and C, then choose a ordered pair. And I'm going to always choose 1. Let X be 1. You can't choose 0. 0 is the easiest to work with, but it's not going to get you anywhere. So don't choose 0. Let X be 1. So here's what I know now. I know X is 1 and Y is a 1994. So this is a X, this is a Y. So your model is Y equals AX squared plus BX plus C. So here we go. I'm going to substitute this X, this Y, this A, and this C into my model. So the Y goes right there. 1994 equals, the A is going to be a negative 6. And the x, if you always let x be 1, that's easy. 1 squared plus, you don't know what b is, so you're going to leave that a variable, but you do know x is 1, b times 1 is just b, so I'm not going to worry about that, plus c, which is 2000. Okay, now, this is going to be pretty easy to solve. So the algebra, this is just using algebra to solve for a variable that you don't know. You got 1994. This is just a negative 6 plus 2000. So that's also a 1994 plus b. So now just solve for b. Minus 1994 minus 1994. That means b is equal to 0. So that means there's no initial speed. So it was just dropped. And we can, the other way we've done in class is this first, but if you look between 0 and 1, its average speed should have been 6, which it was. So that means if it started at 0, its average speed would have been 6, which it is, so it must have started at 0. So your formula is y equals negative 6x squared plus 2000. Okay, now let's do a couple more. I think I messed up on this one. We might have to change some numbers on this one because I think this one is linear and I didn't want it to be linear. So let's skip this guy right now. I think it's just changing by 30 every time. So if you got the linear formula, it should be, yeah, that is 30, so it should be y, and it's going down, so it's negative 30x plus y equals mx plus b. B is a 10 grand. Okay, so let's skip that guy. Let's do this one. Okay, this one, first of all, it goes down 4, but then it turns around and goes up 2. Then it turns around and goes up 8, and now it's going up 14. So that's probably enough to get an idea of what's happening here. So the change from negative 4 to 2, that's up 6, that's up 6, and that's up 6. Okay, so A is going to be easy to find. A is 3. B is the hard one to find. C is 0. So that's nice. C is whatever the y-intercept is. Okay, now I'm going to use the algebra way. I'm going to choose this ordered pair right here. I'm going to choose x is 1 and y is negative 4. So plug it into your model. Y equals a times x squared plus b, don't know what that is, times x. X is 1, so just leave it as b, plus c, and c is 0, so I don't worry about that. So I got a negative 4 equals 3 plus b. Minus 3 minus 3. B must be a negative 7. So my answer, y equals 3x squared minus 7x plus 0. So that means 6, you're on a planet that doesn't have much gravity. Its initial speed was a negative 7, but what happened is it kind of shrunk a little and then turned around and started growing. So the quadratic, you caught this portion of it. It shrunk a little bit, turned around and started growing. That's the picture that you see, kind of like the Nike swish. So if you, let's look at it the other way. So if it's going, changing, increasing 6 feet every second, let's look and see what it should have been. So 0, speed is 0. I want it to be 0. And at 1 second, if it increases 6 every second, the 1 second, the speed is 6. So the average between 0 and 6, the average should have been 3. And the average here was a negative 4, so we got to find the difference. Negative 4 minus 3, you always minus what it should have been, and that is a negative 7. So both ways gives you a negative 7, but you might like this algebra better. Okay, that's it. We'll just leave this alone. I think that is it. Should be good.